Welcome to this video on Moment of Inertia Part 2. In this video we're going to take a look at situations that are approaching more realistic situations, or at least more common situations, where we're looking at moment of inertia. In the last video we defined moment of inertia in a very particular way that I think makes it a lot easier to understand and to connect to, so please go back and watch Part 1 if you haven't yet. We also came up with the generic way to find the moment of inertia I for a point mass m located at some distance r from the axis of rotation. So we're going to take a look at a couple examples here to see how we can start to build up an understanding of more common shapes and how they resist the change in rotational motion. So over here I have a very light aluminum rod. Okay, and this rod is going to have two very dense balls of clay, or you could say lead or something, attached on either end. And I'm going to call this one mass 1 and this one mass 2, and this mass R for the mass of the rod. Now what I'm going to say is mass 1 and mass 2 are the same, and they are much, much greater than the mass of that very light aluminum rod. So this is going to be what we would call negligible. So negligible means that we don't have to consider it because the other masses are so much greater. It doesn't mean we're doing physics land magic and ignoring things. That's not true. We're just saying that it's insignificant compared to mass 1 and mass 2. And you can actually try this out. If you can get a light aluminum rod and two very heavy brass balls on the ends, you'll see that the moment of inertia calculated with the rod is really insignificantly different from the moment of inertia including the masses alone. Alright, so in this case I'm going to rotate the rod about the axis of rotation, and that's really important because what we need to always define is that r is the distance to the axis of rotation to where the mass is located. So this is very important because I could be spinning the rod around this point instead of the middle. So I always need to identify first and foremost where the axis of rotation is. So the axis of rotation, in this case, right in the center, and I'm going to say that this rod is of length L. Now what I can do is, when I'm finding the moment of inertia, or the total resistance to change for this system, what I'm going to do here is say that the total moment of inertia is just the sum of the moment of inertia of each of the objects. I'm going to put here I, all the way to however many you have in a system. So in this case I just have 2. It's also not a vector, so I don't have to worry about anything with those sorts of positions. What I can say here though is that the R value for M1 is L over 2, and that the R value for M2 is L over 2 as well. So when I'm doing this summation here, all I'm looking at saying is I have to add M1 R1 squared plus M2 R2 squared, and then that will give me the total moment of inertia. So over here I could just plug in M1 times L over 2 squared plus M2 times L over 2 squared, and so on and so forth, and eventually I would get a value for the total moment of inertia. As you can see here, the units for moment of inertia are going to be kilogram meter squared, okay, and that we can plug numbers in and solve. Now similarly, if I had added another crossbar of the same length with another 2 masses added, all I would need to do, and I'm just going to add them up here to this situation, I would just have to add M3, and if I said the rods were the same length, then it would just be adding on more and more terms of the exact same length from the axis of rotation. Now of course, if I picked M1 as the axis of rotation, then really only M2 is going to be factored into the moment of inertia, because M1 is at a distance of 0 to the axis of rotation, because it's on the axis of rotation. And this of course is if I move the axis of rotation here. So then my moment of inertia is just m2 times L squared, because now it's located L units away from the axis of rotation. And we can do as many additions as we need to. If we also added a clump over here, well, we just add this. Let's call this one M5, and it's a quarter of the length of the rod, so I would just add that up, M5 times L over 4 now squared, and keep adding as we go. And that would, what we are calculating here, remember again, is the resistance. This is a measure of the resistance to a change in rotational motion. In the next video, we're going to take a look now as the value of R, the rod, approaches the value of the masses. We have to start including it in this calculation. And what's going to happen is that we're going to start to establish other equations in order to come up with a total moment of inertia. Because after all, this is just for a point mass located some distance r from an axis of rotation. So we'll take a look at that in the next video.